Thank you so much. I'm super glad and excited to be here today. There's a lot to talk about, but before I'm gonna thank you all the organizers that for having me. And with that said, I wanna talk about an operation. So I hope everyone here has played video games at least once, because some of the words might actually come in handy from those video games. So today we have an operation and we are in a briefing room. So I'm gonna brief you on operation flow. But before that, I am, as Rashid said, I hope I'm not butchering the name. I'm Seyed Jafari, and definitely reach out to me on my Twitter handle or LinkedIn or GitHub, preferably Twitter, please. Otherwise, just check out my Rusty blog, as the icon suggests, on wordsnast.com. All right, without any further ado, let's see what is a flow. So we should definitely check out the docs, and the doc says a flow is an asynchronous data stream that sequentially emits values and completes normally or with an exception. That's quite a mouthful. I have my own way of understanding things, so let me give you an example that helps me understand. So a flow, uh, let's imagine a pipe. We have a very long pipe. On one end of the pipe, we put events. On the other end of the pipe, we receive or collect or we pick the events. Simple as that. And the pipe is the flow. In the along the pipe, all we can do is just look at the pipe, see the events, or maybe modify them or apply some operations on them. And this is the talk about it. Uh, Before we get into the nitty gritty of the flows, it's important to mention that everything with flows are a stream. So this picture was used to be quite familiar, quite popular with reactive streams, RxJava, but I think it definitely applies to flows as well. So just remember, there is no single event. There is no picking at the very right moment. There is no moment because everything is a stream. You have to go with the flow, put the events on from one side and catch it from the other side. Just keep that in mind when you're working with flows, and it might actually help you fix your mentality. All right, next, let's see a very quick example of how we can create a simple flow and use it. So using flow off, I'm creating a very simple flow with a single event, a string of one, and then with the help of a dot collect function, I can collect that event that has been passed into my pipe. Very simple. But now that we have set it, I need to refresh our memory about coroutines because collect is a suspend function. So this slide is going to be a very much compressed version of coroutines explanation. So please bear with me. Suspend functions are a very special function in Kotlin that tells the compiler, hey, you can only run this function in a coroutine. And what is the coroutine? JetBrains likes to call it a lightweight thread. Okay, how do we create a coroutine? Easy. You just need a coroutine scope, and then you call launch, and in that launch body you have a coroutine. Since we have a coroutine, we can call our suspend function now. Simple as that. Easy, right? I hope it was. Now, back from our detour. So flow by itself is simple. It's just an interface. You saw me creating one and then collecting it. But the thing that comes makes it more interesting is its operators and functions. So we have three types of operators with flow. The first type is builders or creators. The second is intermediate. It's the operators that apply in the middle of this pipe that modifies the pipe for us. And the last but not least is the terminal, the one that we use to collect those events. I'm going to go into details of every one of these operators today. So let's see the first one. Just a quick note, since there are a lot of content that I have to cover, I need to be a little bit faster than other talks. So I hope you excuse me. And if you miss something, definitely quickly just write it in the QA, or reach out to me, or maybe watch the slow version of the talk later when it's recorded. So the first type, it's builders or creators. We already saw one of them. It's flow off. So very easy. You just pass arguments to the flow off function as a parameter, and then it will create a flow and return it to you. The next one is empty flow. So you don't want the flow to emit anything and quickly complete. That's the empty flow you need. The next one is flow with the lambda body. So this is the base construct of flow. When you use this function, you have the full control over the flow, and you can emit the events manually yourself. The next two are callback flow and channel flow. So I'm going to talk about them a little bit later. And if you want to create flow from the list of events, you have as flow. And if you have a list of flows and you want to create one flow from that, a merge is a good function to use. All right. So I told you that there is a channel flow and a callback flow. Uh, what they are actually there to they serve as a bridge that we can use to convert our callback to our flow. So in this case, I have a listener callback, a location listener callback, that I'm listening the updates on the user's location. So using the callback flow, I publish or emit the events, emit the new locations that are provided to me by this unsuccess listener to the flow. Simple. But the thing that differentiates between channel flow and callback flow is that callback flow is just a little bit safer. And by safer, I mean, if you forget to call await close function, you can see at the bottom of the screen, and this lambda just starts reading, okay, I need a listener, register the listener, and that's it without await close. The flow will finish and will never wait for your listener to give it a callback. So it will immediately finish, and you will not receive any events from the flow. To avoid closing the flow, you have to call await closing. And await closing is a suspend function, but you can see the implementation yourself. So a channel flow doesn't force you to implement that. It leaves up to you if you want to do it or not. But callback flow makes sure that you call await close at the end of your lambda. And if you don't do that, it just crashes the app, so you will immediately know what's going on. And just keep in mind, both of these are cold flows. You don't have to worry about it right now, because I'm going to go into very much more details into cold flows and hot flows. But remember, they are cold flows. All right, so the next, we're going to move into the intermediate types. As I've said, so we have the creators, we have the terminals, and we are in the middle. So we want to apply operations. We want to do modify the events that are going through. The intermediate operators are quite long, but I decided to split them in the short segments so I can go through them easier. But the order and the segmentation is all mine, and you don't have to really focus on it. So um, the first part is quite an easy one. So the filter is the first function. Um, Filter, as the name suggests, filters or make sure that the rule you pass applies to all of the events. So in this case, I want to make sure that none of the string events that are passed in my flow pipe is not empty. So filter makes sure of that. And you can see that the result of this filter operator will be just 1 and 2. So the middle event is missing. Cool. So now the next one is map. Again, not rocket science. We just map from one type to the other one. So if the pipe is starting with an integer, we map the events to the string. The next one is with index. It can be very handy if you need to count or have the index of every event that is going through your pipe. And with index is just a short and handy operator for that. It just adds the index to every event that is flowing into your pipe, and you can read it from the flow. All right, the next one is drop, and then after that is take. So I'm gonna explain these two together because they're almost the same. They just do the opposite of each other. So the drop drops the first elements, or I'm sorry, the first events of the flow. So in this case, I'm mentioning drop only one from the beginning of the flow. So the integer of one will be dropped, but the take, on the other hand, will take the first elements. I'm emphasizing on the first keyword because some people like to confuse it with, okay, I'm gonna take the last elements. No, no, no. This is not how it works. You cannot take three. You can only take the first one, or drop the first, which is again one. Just remember about it. And take will take only the first number of elements that you specify, and about the rest, it will just close the flow and you don't have to worry about it. The next one is very useful. So distinct until change is super useful if you want to make sure every event that you receive is different from the previous one. Not from the entire flow pipe, but from just the previous one. So in this case, I have three ones. I take the first one, I collect the first one, but the next two will be dropped because they are equal to the first one that I have received. And then the two will receive, and then again one. You see the one in the second one, I still receive it because the previous event was two. And that is still acceptable. It is very useful when you are creating a final state machine to avoid creating double creating a state. You can just add this thing until changed, and no more duplicates. Cool. The next one is buffer. So buffer is one of those interesting ones. Just skip the on each for now because that's for the introductory purpose of for buffer. But buffer, essentially what it does is that it splits the flow into two parts, the upper side or upstream, or the downstream or the bottom side of the buffer. The reason for that, imagine in this case, collecting a flow. Let's forget that we have a buffer. I'm collecting the flow, and for every collection, I delay the collection for 1,000 milliseconds. That causes the flow emission, the origination of the flow events, to also delay for 1,000 milliseconds. That is not usually what we want. We want the flow emissions to be as fast as possible, and then we will deal with the collection ourselves. So that's exactly what buffer does. It runs the upper stream on a separate coroutine than the collect collection downstream, that which will cause the flow emission in this case goes and emits all of the events at once, but we will slowly collect each event at the bottom downstream. All right, so the next one, I really like debounce. So what debounce does is that imagine that you have a lot of events coming in, but you want to make sure that you receive events in a certain window. So in here, I'm emitting one, and then I'm delaying only for 50 milliseconds, and then quickly emitting another event, which is two. But I'm mentioning, okay, listen, flow, I need a window of 100 milliseconds between each event. And debounce makes sure that happens by checking the difference of the time between two events. So here I have two, I have received two, but the one before it has only a window of 50 milliseconds. So the first event is dropped and only the two is held and then emitted. Then the next one is 150 milliseconds away from the two, so it's still acceptable, and the two will succeed and goes to the collection point. Just in case, if you want to use the bounce for your click listeners, or for when you are listening to the user events, debounce might not be the one that you're looking for because it drops the first event. Usually we want the first click and then disable the button for the rest of the events. Debounce drops the first event, so that might not be the useful operator that you might need. So try to look for throttle first. It's not implemented in the library, but you can do it yourself. It's not that hard. The second part. So on a start is the start of this part. On a start, we'll say, okay, I have a pipe up to here, but all those events are less important than this event. So I wanna make sure that this event goes first, and then the rest of the pipe. All right, that's exactly what on a start does. So as you hear, on a start emits the events before the upstream. So in this case, 5 goes before the upstream, which even has an on a start. But then again, 4 goes before the upstream, and then the upstream starts. I hope that makes sense, but it's quite easy. On each, on the other hand, is like a side effect. If you're familiar with reactive stream or RxJava, on each is equivalent to do on next, except it's a little bit more powerful, because with on each you have the entire control over the flow. So you can delay the flow, you can you, you can print, you can do side effects or delay or make it a little bit slower. So on each does the side effect. In this case, I'm just logging in the console using println, but you can do other stuff. But also on each is a suspending function, so you can run suspending functions. That's why it's a bit more powerful. Uh, Cool. On empty. So the next one is on empty. As we have seen, the filter will just apply the rule, and this rule will just avoid any events from flowing into the pipe. What will happen is that the flow will signal, hey, I didn't emit anything because the filter didn't allow me. If you have an empty operator on your pipe, it will get called, and then you have a chance of, oh shoot, the pipe is empty, what should I do? Should I emit more? Should I cancel it? Should I fire a side effect? That's when the unempty comes in handy. The next one is uncompletion. So uncompletion is useful because it's guaranteed to be called in two ways. If the flow was completed normally or exceptionally, in both ways it will get called. The difference is that if it was completed normally, the throwable parameter passed to you is null, and if it's null, you can actually emit more values to the downstream. But if it wasn't, there was an exception happening in the flow, and that was the cause of completion, then you cannot really do anything, and the flow is already stopped, and no more emission is allowed. So definitely use it, but be careful of this law and make sure that you check the throwable. Oh yeah, one more thing. On completion that I forgot to mention, on completion is not the best place to free up resources. So if you have a socket to the server connected and you want to close the socket in on completion, that's not the right place. Make sure you do it with when you're creating the flow, not in here. So that's also worth keeping in mind. The next one is retry, when, and catch. I put this together because I think they're very much connected. So imagine that the flow on the upstream throws some sort of exception, literally anything. And you want to make sure if any exception happens, you just want to try a bit more. That's when retry when comes in handy. So it gives you the exception and also the number of tries it did, and you can decide, okay, do you want to retry the flow again, or you just don't care about it. So in this case, I'm gonna try 3 times before I give up on the upper flow. And of course, because each time I'm throwing an illegal state exception, it's not gonna pass. So the retry when will not succeed, even after trying 3 times. But the next operator is catch. So if there is an exception on the upstream, you can catch that exception without affecting the downstream in catch. So catch will give you the exception, also will allow you to emit new events in case that there was an exception. So you can kind of convert that exception to another meaningful object and return it to the downstream. Just very important note here is that the catch will only work on the upstream. So anything happening below catch will never know about it, and only will catch the upstream exceptions. All right, so moving on to the part three, we have flow on. So flow on is the only operator that allows us to change the dispatcher of the upstream flow. It's very simple. You just pass it to the dispatcher, and what is happening is that the upstream flow up onto the previous flow on will work on the dispatcher that you provided. So what I mean by that is that the flow off function will work on default dispatcher, but the next dispatcher IO will work only on each. So it will go one function back and see it's on each. Okay, fine. We apply IO dispatcher on that. And then it will go to the previous operator and sees, oh, okay, so we have another flow on. Sorry, I'm not going to apply IO dispatcher on that. And so with that, on each will only be, is the only operator running on IO dispatcher. Good to keep in mind. Next part. So this one, a transform. Transform is, I think, by far arguably the most powerful uh, operator in Flow, because basically it provides you with all the power of the flow creation. And if you look at how it's been implemented, it's nothing rocket science. It's just creating a new flow and collecting the previous one. But the reason I'm saying that it's very powerful is because most of the other operators are built on top of transform. And if you check it, if you check my example here, you can see that I'm filtering events. I'm checking if they're not empty. And if they're not empty, I'm firing a suspend function, getting the result and emitting new values. So your hands is wide open to do whatever you want when you're in a transform. Um, cool. The next one is zip. So we want to literally zip two flows together. To do that, we just use zip operator. The way that zip operator works is that it takes the events from the from one uh, sorry, from one flow, and then waits for the other one to emit one event as well, and then gives a callback to you in that lambda, and then you can decide whatever you want to do with those events and return from that function. And the zip will return another flow. Just a very important thing to keep in mind with zip is that both flows need to emit the same number of events in order for this lambda to work. So if one flow emits, let's say, 10 events, but the other one emits only 5, the other 5 of the first flow will be held until there is a corresponding event from the other flow. Just make sure that you have same number of events for the two flows. If you don't have it, it's fine. There's another operator. It's my favorite. It's called combine. So combine will do the same thing with zip, except that if the number of events don't match, it just uses the previous events from the other flow. So in this case, there is only one event coming from the fetch book list flow. There's only one event, and it's a list of books. Fine. But then the query name flow changes rapidly. So the user is continuously typing in the keyboard, and it gives me a new query to search for the book names, right? So the flow is constantly emitting new values. In this case, combine gives me the new query with the previous book list that I've fetched from the server, and it doesn't go and fetch it. It just cache it and it gives me again. So I can just operate on the original books list and filter on it based on the user query. Awesome. So here comes the flat map. This is the favorite slides for interviewers. They usually ask a question about flat maps. And we have 3 types of flat map: merge, concat, and latest. So quickly to explain what a flat map in general is that let's remember our pipe again. So we have our main pipe that our events are going through, and then we add a flat map, either one of these 3, any one of these 3. And then what flat map does is that it creates a sub pipe. It does some operation, and then puts back the events that are generated by that sub pipe to the main pipe. That's exactly what it does. So you just create subflows. Those flows do their operation, and then those events can be collected from the main pipe, not from the sub ones. If that doesn't make sense, let me go through them again, and maybe this helps. So here, the first one is flat map merge. We have three events going down our main pipe. For each event, let's say for an event number 2, we create a new flow. We do some operation in that flow and return the flow. So the collectors who are listening to the top flow off will receive all of the events from the sub flows. All right. The difference between flat map merge and the others is that flat map merge doesn't respect the order. So you can see as as the result, you can see A1, A2, A3, but it's not obvious what's it gonna be, B1 or B3, B2 or B1. You're not sure which one is going to go first, because flatmap merge runs all of those subpipes in parallel, and you wouldn't know which one might finish. It might be the second one, it might be the first one, so you wouldn't know that. But you will use the maximum concurrency available with using flatmap merge. If the order is important to you, so you want to make sure that the subpipes run in the same order and will emit in the same order as the main flow, you can use flat map concat, which you can see in the result. You have A1 and then B1 and then A2 and B2. Just keep in mind that in here we don't do any concurrent operation, because the flow, the sub pipe has to do its job, finish up, and then the next event will take on to the will be passed to the sub pipe again to do its operations. And that's how the order is preserved. The next one, I really like this one, and I happen to use it a lot when I'm working on MVI-ish architectures on Android. It's super useful. But other than the MVI architecture, you can use it in different places. So imagine we have a database that we are observing by a query. So a user types in a query, and for every query, I want to observe the database. But it doesn't make sense if I keep observing to the previous queries, right? That's when the flat map latest comes in handy. So for every new event that comes from the main flow, the sub pipe that is generated, the sub flow that is created will be canceled, and a new one will be created, right? So in this case, I'm listening to the database for the query A, and then the user types query B. The previous observation to the database will be canceled. Then I start observing the database using the query B until the next query comes in handy. Again, they're not very hard. Just give them a try. You will see how they can be handy in your cases. The fifth part, I think this is the last one. So we have reduces, and there are two versions of them, running reduce and scan. So reduces kind of go hand in hand when we are creating FSMs or finite state machines. And let's see how they work. So reduces allow to accumulate the returning result of the lambda. So in this case, sorry, just keep in mind that the first event that it goes through the main flow or pipe will be passed directly down to the downstream, because we don't have a previous accumulator before that. So in this case, one immediately goes down to the downstream, but now we have an accumulator so for the next event, we have 2 as the value and 1 as the accumulator. And then we do our operation, which is multiply. We multiply that and return it. So 2 will be passed to the downstream and also cached as accumulator for the next event. That's how running reduce work. If you want to modify the first event that I told you that goes immediately past the reducer, you can just use a scan. So with a scan, you can pass the initial event from outside of the flow, I mean. And then from that moment, all of the other events that are coming from the flow will be accumulated, oh, I'm sorry, will be operated on the initial event or state that you passed in. This is very useful when you're building states for your UI and you want to build the state based on the previous state that was on the UI. So you have the previous state, you have the new action, you apply the action on the state and you create a new state, and then you also catch it. All right, so we're done with the intermediates, and now we are to the terminal. So now we want to pick or collect those precious events that are in our pipeline. Terminals are not that long, so we have a number of them here. We're going to quickly cover them. The first one is collectors. I think they're the easier ones. So you just write collect. This is like the basic way of collecting a flow. It just gives you the events one by one. Collect index is like using with index and collect. It's just a handy, easier function to use if you want those two to be connected. And the last one is launching. So if you don't care about the events that are going downstream, if you don't want to collect them, but you want to launch the flow, then just use launch in and pass the scope and done. You're done. The flow will start working and it will just run from the start to finish. The next one is collections. So you want to convert your flow to a list. So you have you have events coming down the flow pipe, but you want to convert that pipe to a list. You can use two list or two set. Those two will do the job. Just make sure that you don't apply them on the hot flows because they will never end. I'll talk about hot flows later. Just keep that in mind. First, um, we have two collector operator for flows, a single and first. So single tells the flow, okay, I want only one event from you, and I don't expect you to emit anything else. If you do, I'm gonna blow up. First, on the other hand, says it's fine if you have 100 elements. Just give me the first one and I'm done. So that's how they play. Both of them has their own place, but just keep in mind the difference. Of course, we have also the reduces as the terminal operator. So the reduces in the intermediates return a new flow. So you have a new flow and you can do more operations after the reduces. But here in the terminal, they don't return a flow. They just return a single value. So here in this reduce, you will just receive 6 as the returning result of this terminal operator. We have also the corresponding operator to the scan, which is fold. You can pass the first accumulator yourself from the outside world. All right, so we covered all of the almost. There are a lot of them, but the other ones are kind of modified version of the ones that I spoke about. Right now, let's talk about cold and hot flow. Some people like the weather to be cold. Some people like to be like the weather to be hot. I mean, everyone likes it to be hot, right? The weather is a good example of what we are talking about. Learning which flow is hot and cold was always hard for me because those concepts are not close, at least. So I came to an example again for myself. Let's imagine, forget about the flow, forget about all we talked about now. Let's focus here on these two. Imagine that we are in a boat. When we are starting to row, the boat starts to moving. When we stop, when we stop the bowing, the boat stops too immediately. So it has our bowing has direct effect on the boat movement. Easy. On the other side, we have a car engine. When you start the car engine, it doesn't stop. It doesn't stop until it. Uh, let's forget about that until. So when you start a car engine, it just starts working. and it doesn't care if your engine gears are connected or attached or engaged or not. It just works. You can use the power created by the engine, or you can just let it run idle. That's exactly the difference between hot flows and cold flows. So the boat and the Boeing is the cold flow. I see some feedbacks. Great. So some people maybe got it. So cold flows are like Boeing. When you collect them, they start working. And when you stop collecting, they also stop. But the hot flows are like car engine. So when you start the hot flow, I'll tell you how, they will start working, whether you're collecting or not. They don't care about you. They just do their job. Uh, that's basically the difference between hot flow and a cold flow. And all we have been talking about so far, 33 minutes down the talk, it was just about cold flows. Now entering the hot flows. There are only two types of hot flows here. So we have shared flow and state flow. Simple. The both of them are built on top of normal cold flows, so they inherit all the powers, all the operators, and all the behaviors, almost all the behaviors of the normal cold flows. Just keep that in mind. All right, so let's look at the first one. You can create a shared flow using its mutable shared flow factory function, or if you have a cold flow, but you want to convert it to a shared flow or a hot flow, just call sharing, and immediately it will be turned into a shared flow or a hot flow. The parameter that is passed as sharing started, I passed eagerly. That parameter specify whether you want to start collecting from that cold flow immediately, or you want to wait for the first collection and then start the hot flow. Remember, the hot flows, when they start, you cannot stop them. They just run forever. So this just specifies when the starting point happens. A good use case of this sharing is that, let's imagine that you have a socket connected to your network backend, backend over the network, and you want to, and that flow, and there is a flow on top of that socket. That flow is cold. So when you listen to the start collecting from the flow, the connection is started. When you stop, then the connection is destroyed. But you want to share, because the network operations and listening to a socket for apps can be costly, and you want to share the events that are coming from the socket, right? Hopefully. So what you can do is that share that socket flow, which is called, with multiple collectors. That way, you're not wasting more resources just by creating more sockets to your backend. Just only one socket is created, and the events are shared with all the collectors. You can emit values to this hot flow, to this shared flow, using dot emit, which is a suspending function, and so you need a coroutine and a scope to run it on, and also try emit. My preference is always to go with emit because it's safer. It makes sure it waits, suspends until the right moment, and then it passes the event to the flow. If that is definitely not the case, then the try emit is an option for you. But just judging by the name, it actually suggests that it will try. It will not make sure that it's passed down to the flow. So preferably used emit. The next one is a state flow. So all I have said up until this moment, did I say correctly? Oh, yes. Was about share flow. They exactly apply to state flow. Actually, state flow is built on top of a shared flow. There's only one difference. State flow caches the last event and replays it to the new collectors. So there is only one value in the immutable state. Sorry, in the state flow, that whenever a new collector starts collecting from this state flow, it just passes that value to the collector. It comes in handy when you have. I usually use it the state flow with my UI states. So I want to give the UI the last UI state to the view layer of my application architecture. So state flow is the best candidate here because it keeps the last event and it passes it to the collector as soon as there's a new collector. Again, exactly the same as how shared flow works. You have emit and try emit, but because we have only one value, we can also use dot value and pass our argument as to this parameter. Just remember, again, I suggest to use emit here as well. All right, so we cannot come here and talk about a technology and not cover the testing part, right? Usually there's a saying says that no test, no talk. I hope there is one at least. So here, testing a flow is not as scary as it looks like, right? So if you have a normal cold flow, easy. Just convert it to a list, and then you will receive a list of events that are passed, and then assert or do the operations on the list normally as you would do in old JVM times, right? But if you're in a hot flow, and if you have a hot flow and we want to test on top of a hot flow, then the story is different. Because if you remember, I told you that two list and two set does not work on hot flows. And thanks to our beloved developer, Jake Wharton, and his company, not his, but the company is working, Square, they have a library for us called Turbine. Turbine. So if you have a shared flow, just use the library, and then there will be an extension function called test. Use the function, and then in the lambda, you can call expect item. So the expect item will give you the events that are emitted by the flow in the order, and you can assert on them. If you don't want the remaining items, you can call cancel and ignore remaining events, and the test block body will finish, and the main run blocking will also finish. So that's definitely helpful and handy if you're testing your flows. If you want to see some of these operators in action, definitely check out. I have a project called Rion. Definitely check it out. It's on MVI architecture. It's multi-platform. The whole app is built on top of a uh, multi-platform in mind and flow operators. So I think it's worth checking. But if you forget some of the operators and you want to quickly remind yourself of what did that operator do, definitely check out flow marbles. They are useful. It might get time a little bit to get used to how flow marbles work, but when you do, then it will be much easier from there on. That's it. Operation successful. You're all now briefed. I wish you all guys a happy flowing. Again, reach out to me on my Twitter handle or in LinkedIn or anywhere you feel like it. We are hiring in very large range of positions in Revolut. So if you're interested to working with me and lots of other very talented people, definitely check out our revolut.com and careers page. That's it. Have fun. All right. So the first question. Um, is there any operator which gives mediator live data like behavior? So I don't remember. I'm gonna be honest here. I wasn't a fan of live datas, and so I didn't use them much. There was always XJava and Flow for me. So I don't remember exactly what the mediator did, but if I remember correctly, they would combine two live datas and then generate one. If that is the case, you can come up with a question later up. But if that is the case, so if you want to combine two live datas and then return one, I already showed you have zip and combine. So those two can be handy. If I got the question wrong, definitely reach out to me after the talk, and I'm happy to discuss it. All right, so Shalom, you're asking questions. Are you supposed to? Does first let the flow complete after the first value is emitted? Yes, exactly. So when you receive the first event using the terminal operator first, then the rest of the flow will be completed immediately because you're not collecting anymore. It's immediately uh, over or completed. Huh. All right. So does the stateflow survive config changes in Jetpack view models? So that doesn't do anything. That doesn't have to do anything with view models or surviving config changes. View models in general, if you create them in a right way and you use them correctly, they will survive the config changes. And so all of the objects that are inside them. So if you have a state flow inside the view model, exactly the same as how the live data work, it will survive the config changes. So that's why I said it. Stateflow is usually a very good candidate for when you are publishing new view states to your view layer. So yeah, yes. Is there any way to filter common values in flow? Uh, by common values, you mean the ones that are keep repeating without being adjusted? If yes, um, then we have operator called distinct. I hope we have it. I think we do. I think we do. We have a protocol distinct that it makes sure that every event that you're receiving is unique. That's the only thing we have. Other than that, you have to come up with your own operators. And frankly, it's very easy to create operators as opposed to RxJava. And this is one of the best things I love about flows. RxJava, creating a new operator for RxJava was rocket science. It was super hard. If you check out their GitHub page, it's just super long explanation of how. But with Flow, we just create an extension function and boom, you're done. What's better to convert Flow to live data or use Lifecycle Observer to collect it? What's better to convert Flow to live data or use Lifecycle Observer to collect it? Okay. I'm not too sure. There was a, I don't know about this answer. I'm gonna be honest here, but I think, please don't take my word. I think they don't have a much of a difference in normal Android view system, but in Compose, there was a big difference between those two. There was a discussion going on Twitter, but I don't remember exactly what was going on. So I'm sorry. I don't know. Hmm. Where do you use flows in Revolut app? Are there any use cases in Revolut app when you need to share a state on different places or are you using channels? So as far as I'm aware, we're not using any channels, but we are extensively using flows. And the entire architecture also in Revolut is built on top of hot flows and flows. And everything we do is using flows. So I think that answers the first part of your questions. And are there any use cases in Revolut app when you need to share a state on different places? I don't really understand that. By different places, I don't know what you mean. So maybe just elaborate a little bit more. Should I use a state flow or shade flow to implement any filter by terms feature? The user takes as something and I filter a list with this term and why? Should I use a stateflow or shadeflow to implement a filter by terms feature? Uh, I try hard to understand it, but I'm failing at the moment. So, um, should I use a stateflow or shadeflow to implement any filter by terms feature? I'm sorry, I don't understand it. Sorry, I tried hard.
I think those were all the questions for now. And And if you want to explain a bit more about your question, probably explain it more to Shed. You can definitely join the. Definitely after this join the speaker table. And thanks, Shed, for the wonderful talk. It was really interesting to learn so much from you. And
Thank you so much.
yeah, that's all for today.